So what I want to, so the main thing I want to do today is kind of try. I mean, well, a lot of the point of this course is really kind of to develop the background that you needed to understand what the elements are of our kind of best understanding of kind of fundamental particle physics of the Standard Model. And so I've kind of gone as far as one can go, I think, you know, without getting into some much more complicated material. But what I wanted to do today is just kind of go over, kind of give an overview of what the Standard Model is, and explain, show you kind of which pieces that you should are things that we've discussed that you should always understand, and then which things of it you're going to need where, you know, some new ideas are needed to really to understand what's going on, and at least give you kind of you know, a quick summary of what those are. So that's the plan for today. Okay. Okay. So let's see. So the maybe so. I think so. One can start at any different at different places, but let me start with this. Let's see the okay. So the first. So the first part, the first component of this of the Standard Model is these local these gauge symmetry gauge symmetries. And what I did was try to explain in some detail what a U1 gauge symmetry is, and how there are these corresponding gauge fields, which are the standard kind of vector potentials of, and it's the standard theory of electromagnetism. When you quantize the theory, you get a theory of photons. So we kind of went through all that, and then at various points I tried to kind of explain or mention a little bit about what happened if you tried to generalize from the group U1 to say to the group SU2. But what you find is that you have in the Standard Model, it involves this U1 theory that that we really pretty much covered in detail, and it involves a separate SU2 story, a separate SU2 symmetry, and separate SU2 vector potentials. So these are things that are valued in the Lie algebra of SU2, and they're and I gave some examples of the formulas for this. But then there's also an SU3 story. There's also an SU3 story, and this I didn't kind of say anything really specifically, but it's really the formulas that you write down pretty much wherever you're using the Lie algebra of SU2. You use the Lie algebra of SU3. You have the Lie algebra of SU3, and so here it's this is three-dimensional. Well, here it's one-dimensional. You get one kind of gauge field, it's the photon. Maybe just write these down. More or less, what's happening is here you have the photon. Here you have this Lie algebra is three-dimensional, and you have corresponding gauge fields and particles, which are W plus minus, called the W plus minus and the Z. And then in the for SU3, you can see that the group is 8-dimensional, and the Lie algebra is 8-dimensional, and so you're going to have eight corresponding gauge fields, and these are called called gluons. Okay, and so let me kind of say a bit about what happens when you try and calculate with these things. So the maybe a good thing to say is just to write down the Hamiltonian. So H, let's see, I just want to write this down. So H is just the sum, over three things. Let's say J is equal to 1 to 3, and the three things are half. Or 3, and then so So when I do this, I'm kind of burying all of the complexity of these guys in the notation. That for this is a sum for actually I guess I should call it. No, sorry, I should call it here. I have to have a trace, and then for the trace of J means trace here, which is just the usual thing, or here is that. Anyway, it's just the trace of these in these Lie algebras as matrices, and then these guys have to have an index J, I guess. So for J is equal to 1, I just mean this guy, you know what it is. For J is equal to 2, the formulas are just these things live in the Lie algebra of SU2, and you have to have an invariant inner product on the Lie algebra of SU2. That's the trace, and then you do the same thing for SU3. Okay, now the problem, okay, and now when you do this, also embedded in here, I guess, embedded in here is there's a choice of normalization. And so you have constants. And so what you had when we were just dealing with the U1 theory, there was this one constant that appeared called E, and that's basically this guy. And what you can put that constant either in the covariant derivative, or you can put it here in the Hamiltonian. It just depends upon how you normalize the field. And the normalization I've used, it doesn't, you don't explicitly see these constants here. You see them in the covariant derivatives. But if you, but the kind of origin of your ability to have three kind of independent constants governing what's going on, it comes about because you've got kind of three independent inner products on here, here, and here. And you only know they have to be invariant under the group. They have to be adjoint invariant, but they don't. They have to be invariant, but they don't. You don't know what there's nothing fixing their overall scale. So there's kind of three extra. There's kind of anyway. There's kind of three numbers here that are buried in the calculation somewhere. I'll call them this, and those are going to govern the strength. You know, one place those can be made to appear is in the covariant derivative, and then they're going to govern the strength of the interaction of these gauge fields with whatever particle that they're interacting with, where you're using that covariant derivative to get the interaction. Okay, so now so as I kind of mentioned, the problem so what's happening here. So maybe it's best to understand what's going on. You can always just go to a zero gauge. Okay, so I'm always going to make the time-like gauge field equal to 0 just so we can always make that gauge choice. And then you have that E vector is minus the A vector dt. This is fine. Okay, and now the only difference, so you've just got, and I guess I should put J's here for, and so for each of these cases, you have a corresponding vector potential which lives in the Lie algebra of these guys, and then you have a corresponding E field which lives in the Lie algebra also, and it's just the time. Anyway, it's just the time derivative of this guy. It's just it's kind of the corresponding momentum, if you like, in terms of the phase space formalism. But then the tricky one is this guy. Is the magnetic field, and then so the magnetic field is then always going to be basically you can write it as the curl of the A vector. But the tricky thing is that the curl now should be a covariant derivative. So there has to be so this guy is not just the usual derivative. So del A is basically del minus I E A. Or so it's, yeah. And anyway, so it looks like this. It's it's kind of the appropriate derivative, covariant derivative acting on the A's, and the A's are adjoint valued. So you need to include the effect of the A, which is telling you what happens when you parallel transport. Well, if you parallel transport in the adjoint, if you do an infinitesimal parallel transport in the adjoint representation, you're taking a commutator, so you have some kind of term like that. Okay, and so what this means here, then if you look at this, is that there's now a okay. So anyway, the problem is that you now that you got the problem is this term, and I guess I should put a there's a G sub J or whatever. So the problem is that so in the U1 case the commutator is 0. So in the U1 case you don't see this at all, but in the SU2 and SU3 cases you have this term to worry about. And then what happens? Then what happens here is that if you so here this term is just quadratic. This term is quadratic in the A's, but this term now, this guy is now kind of grad A plus A squared. So this term has it has things that are pieces are quadratic in the A, but it also has pieces that are cubic in the A and that are also quartic in the A. Because you've got you're squaring, this is acting on an A and then you're squaring it. So the cross terms are cubic and the square term involving this is quartic. So this has terms that go as A cubed and is A to the 4th. Okay. So this causes a huge amount of trouble with we've been trying to do. What we've been doing is trying to tell you that everything is just a bunch of harmonic oscillators, and we're just doing an infinite number of harmonic oscillators. But that all relies upon the Hamiltonian being quadratic in the fields. So as long as you've got Hamiltonians that are quadratic in the fields, we can kind of reduce everything to harmonic oscillators and solve it. But now these terms, this guy has messed this up. So and if you you no longer have if you try and write this in terms of oscillators, you no longer have decoupled oscillators. You have oscillators, all of which are all interacting with each other and with this. Okay, so that's the kind of fundamental problem. Okay, so what can you do about this? Well, this is fun. So so the problem is gonna be of a different nature for these two guys and for this guy. So what the basic fact is that the kind of physically relevant numbers for these guys is that these guys are relatively small, are significantly less than 1. This guy is well, anyway, let's just say that he's not always less than 1. So for the interactions of these guys, the kind of electromagnetic and weak interactions, you can try and develop a calculational method where, based upon these guys being small numbers, but for the strong interactions, that's not going to work at all, because this guy's the relevant version of this guy is just not a small number. Okay, let's just say so the big kind of hole in what I've been doing in this whole course is that it is kind of not telling you, how to do these calculations in general. But the main thing which you would learn in an ordinary course is the so-called perturbation theory. So perturbation theory is to you expand it's a method for calculating terms in a power series. Expansion in G. Okay. So if the idea is that if G is small, we can expand about G is equal to 0. If G were equal to 0, then we would just have everything would be quadratic. It would be our nice decoupled oscillators. We know what to do. And so the idea is that we want to kind of somehow expand in powers of that and assume that this is small and get some kind of get some answer which doesn't give you the full understanding of what the theory is saying, but it gives you an understanding of what this is saying, kind of to lowest order in G and to the next lowest order in G, etc. And that okay. So I'm not going to say too much about this. This typically this is the diagrammatic version of this involves Feynman diagrams. And you and one complication is gauge symmetry. And so, as I kind of mentioned as we were going along when I was talking about gauge symmetry, in the U1 case, there are various ways of handling it. There's like you can go to Coulomb gauge, or you can do use an indefinite inner product and do a covariant gauge quantization. But if you try and do it for the nonabelian cases, for the SU2 or SU3 case, the methods that I told you about actually don't quite work. So you have to develop new methods, but these new methods can be made to work for the perturbation series. So to any given order, you can develop a method which will properly handle the gauge symmetry at that point. And so this involves in things called involves introducing new fields with the wrong statistics called ghost fields, or and sometimes also maybe you could fit from the path integral point of view. It's sometimes called the Faria-Popo method. Okay. So you can do that and in principle calculate things to any order. But then the reason that I didn't develop this perturbation series method was not only that it's a bit complicated to set up all this calculation correctly, but the problem is that even once you've done it, is that you you get a basic problem of principle. And so what's called and which you have to treat by what's called the theory of renormalization. Okay, and so what I maybe a thing to do is to say that so naively the terms are infinite. So if you try and develop this perturbation series, and so when people first did this in the 1930s or so, what they did, they started writing down these perturbation series expansions. They started calculating the terms of the expansion, and they found that the coefficients of the various terms in G were just often infinite, but there was some kind of integral which diverged. And so I think at that feeling in the 1930s, the general assumption was that what this meant was that quantum field theory actually didn't really, was just some kind of low energy approximation that you couldn't actually, it wasn't something that really made sense as a real fundamental theory. Then what happened in the 1940s and 50s is people figured out ways, at least within the, within this U1 theory and later on for the SU2 and SU3 theories, how to actually make sense, how to make sense of these terms in the perturbation series. But it's kind of tricky. What you need to do is you basically need to put in cutoffs, make the theory, the integrals finite, and then to take the limit, and then you need to choose. And let's in particular you need a, let's put some number called gamma UV. You need to have some kind of highest possible energy or smallest possible distance, and to not allow degrees of freedom smaller than that. And then what you do is you then you try and take this guy to infinity, or the scale down to 0, and you need to take G of lambda UV varying lambda UV so as to get physical, to get sensible result. And maybe just the last thing to say is that the limit is very singular. I mean, there's a long story about this, and this is kind of why I never didn't want to get into these thickets. But this is kind of one way of thinking about the story, is that if you actually another aspect of the problem besides the nonlinear, something related to the nonlinearities, is that remember that when you had a finite number of degrees of freedom, you had the Stone-von Neumann theorem, which says that there's really only kind of one, there's really up to unitary equivalence. There's really only one representation of the Heisenberg Lie algebra, or there's only one representation. There's only one way to do canonical quantization up to a unitary change. Well, what happens is that maybe it should say this here. So Stone-von Neumann fails in infinite dimension. Okay, so if your phase space is infinite dimensional, well, it turns out in this limit, as you take your phase space to make it infinite dimensional, you can get all sorts of different unitarily inequivalent representations of the Heisenberg commutation relations, or of the Heisenberg group. And so this business about that there's really only kind of one. You didn't have to worry about the representation of this group, but or of what your state space was, because there's only one sensible way of doing it, up to unitary equivalence. That's no longer true. And so what's happening here is that as you if you put in the cutoffs like an infrared and an ultraviolet cutoff, then instead of a finite number of degrees of freedom, then Stone-von Neumann works, and you can anyway, you can write down a perfectly sensible thing. It's not a bunch of decoupled oscillators. It's a bunch of coupled oscillators, but it's a finite collection of coupled oscillators, and there's really only kind of one sensible way, only one way to quantize that. And then so then you just have to use the perturbation expansion to tell you how to deal with the fact that these oscillators are interacting, and if they're interacting fairly weakly, the perturbation expansion can be good, and you can do the calculation. But then, as you take the limit of the cutoff going, say the ultraviolet cutoff going to zero, take it going to zero, and you get an infinite number of degrees of freedom, then what happens is your problem is that you're gonna the limiting theory you get is actually not going to be a theory of interacting oscillators of the kind you're used to. It's going to be it can be something quite different, and also there isn't any kind of nice theorem saying here's all the possible things that it can be. So that's just the beginning of okay, and then the anyway, this is just an outline of the problems that you get into. Let me see what else I wanted to tell you. So maybe a standard. So there's a standard belief. I actually, to be honest, I've never been able to get I never can find a straight answer as to whether this is actually a theorem yet or not. People keep saying that this is a theorem, but only up to maybe believing something very plausible. Is that for scalar fields? In 4D, the limit is always a non-interacting theory. Okay. And so that's it. Anyway, there's a story about that. But anyway, if you believe this kind of very standard, supposedly well-motivated conjecture, what it's telling you is that if you just tried to take the story that I told you about the Klein-Gordon equation scalar fields, and you tried to add some higher order terms to the Hamiltonian, basically, if you tried to go through this process, and if you added these higher order terms to the Hamiltonian at a fixed cutoff, then what is going to happen as you take the cutoff down to zero is that no matter how fast you make these, no matter how fast you try and jack up the interaction strengths as you go down to smaller and smaller distances, you're not going to get in the in what you see at long distances, you're not going to get any interactions. You're just going to get a free theory in a limit. That's the belief about that, and for a long time, again, up until the early 70s, it was believed that this was true for all quantum field theories, and this was also a reason for a belief. If you looked at what people were doing in the 1960s, there was also a typical belief was that quantum field theory was actually not, again, quantum field theory was not could not be a fundamental theory because even though in the 50s you had found out how to make sense of these terms, that it really didn't matter that if you that the full theory always had to have some problem in the limit as cutoffs went to as a distance cutoff went down to zero. Okay, but now for the gauge field. So what happens for G? So for G1, for the U1 factor, that has a potential problem like this, which but anyway, it somehow only occurs at exponentially small distances, or so you're not sure what to make of it. But for gauge fields, for let's say non-abelian, gauge fields, so as lambda UV goes to infinity, G lambda UV goes to 0. So these are what are called asymptotically free. Okay. So for things like the strong interactions, what we believe now happens is that the theory, what happens is if you make a cutoff of the theory, like you do what the people in the physics department are doing with their lattice gauge theory calculations, you write down this theory of strong interactions, put it on a lattice with a fixed lattice spacing, choose G, and then try and take the lattice spacing down to 0. You have you don't have the problem of having to try and crank up the interaction more and more to get something non-trivial. You have the problem. You have the opposite problem. You have the problem is that you don't. In order to get something non-trivial at long distances, you have to take the short distance coupling down to 0. And so what this is telling you is that this is a theory which has actually, as you try and understand what's happening at shorter and shorter distance scales, given the fixed physics at long distance scales, if you try and look at seeing what's happening at shorter and shorter distance scales, you've got it's approaching a free theory. It's approaching a theory of uncoupled oscillators. So this is what we believe is true for this SU3 factor, that for gluons. What we believe is that as the story about gluons is that they're very hard to understand at long distances. We're in the infrared, which is when we're kind of observing their long distance effects, and that's because this is getting large, and we can't use perturbation theory. But as you go to shorter and shorter distances, their gluons are behaving more and more just like the uncoupled oscillators that you expect. And this you can actually see. So you do when you do collider experiments and you probe shorter and shorter distances or higher and higher energy scales, you then see you start to see that the behavior you would expect from weakly interacting gluons, from gluon states. Okay, so that's so this is the story about okay. So this is pretty much so this is the well anyway. Let me tell you before I go on. Let me tell you one more thing about gauge fields. So what's the problem? If you can, maybe I can give you a precise. So let me just say kind of the essential problem. And so maybe let me so you can kind of, I think you can kind of localize a bit what it is that we don't understand at all about these theories. And then this is the problem that's this is the so-called Millennium Prize for Yang-Mills theory. Mills. That's let me say the mass gap. So there's $1 million associated with this problem, and I think that the reason why it's an open problem is that we really don't. There's some essential idea missing as to how to really say this. What you could do is just take. So you consider. H. So what you do is take the and this is true. The problem is even for SU2, nobody even really understands how to do it for SU2, much less for other groups. But let's take the so the configuration space is A of X vector, and so these guys are it's all of the kind of SU2 Lie algebra valued functions on R3. Okay, and what you can do is put a anyway, and anyway, take this as your configuration space, and then take the and then the Hamiltonian is equal to what was it? It was a half the integral and for R3, and now you had an E squared term, but remember the E squared when you go to if you realize your states as functions on configuration space, then the momentum just becomes the derivative on configuration space. So you want something like a derivative on, I want to say it, E is, E delta A of X vector squared plus this is it. So you let me just put it better. So you can think of this Hamiltonian operator as an integral over some density. And this density, these guys are just acting as multiplication operators on the coordinates on your configuration space. And this guy is just a differentiation operator. So one problem is that there's two problems. Problems one are well, you have to go with gauge invariance, and then but two you have to define as a limit. Okay, but the anyway, so the way I've written it, you've got this group of time independent gauge differentiations that are still acting on it. You have to somehow quotient out by that. But anyway, ignoring that problem, your problem is really just here's a space, the space of all SU2 gauge fields at a given time, and here's an operator on that space, and you just have to you have to make sense of like what's the appropriate notion of inner product on this space, and so what you're going to have to do is really probably put in cutoffs, define the theory with cutoffs, and then get something sensible on the limit. If you could do that, all of our belief is that you actually can do that, but we don't have. And we have plenty of evidence, numerical evidence, that if you try and do something like that, you should be able to get a sensible limit. But we don't actually have any mathematical proof that the limit really exists. That there is a limit that exists that has the properties that you want. So it has to be kind of rotationally invariant, and it has to have some non-trivial physics. In particular, there should be a invariant vacuum state, and there should be a lowest energy state above the vacuum with a fixed mass of some kind, and you should be able to find that. But this is the problem. So I just wanted to kind of this is something that I'm not getting at all close to in the class, but maybe you can kind of see that it is kind of infinite dimensional generalization of something fairly close to what we have talked about, and it's kind of this is something that's kind of at this point kind of seems to be significantly beyond what anybody understands how to do. Okay. So that's maybe that's the story about just about pure gauge fields. So if the world were just a world of photons, W and Z particles, and gluons, this is pretty much all. I would have told you the entire story of the Standard Models and such. So this is kind of, but these are the things which are, in some sense, cause forces. Okay, so let's go on to the next part of the story. Next one. So this is so two. There we go. So our best understanding is pretty much all of the what we think of as the matter particles in the world are all kind of they're all spin 1/2 particles, and they're all obey the Dirac equation. And you can and so they maybe the thing to so all you need to really do is to say so all matter is spin 1/2 kind of, let's just say, vile particles. Let me just say spin 1/2 particles obeying equations. But the Dirac equations, remember, so d slash so these if it weren't for the gauge fields, well, as far as the fermions are going to be concerned, we're never going to have we're only ever going to have quadratic terms in the Hamiltonian or whatever, and it's always going to be linear equations in terms of psi, and the Hamiltonian is always quadratic. But the problem is going to be that the interactions between matter are caused by the fact that you take in the Dirac equation you have this d slash thing, the d operator times with these gamma matrices, and then that goes to a covariant derivative slash, and so you get an extra. Anyway, so this term, so you have added terms in your Dirac equation, which couple the spin 1/2 fields to the gauge fields. Okay, and as far as if you and then maybe let me actually write this out like I did in the notes. So you have H, it's just the 1 over R3, and then you have now the point is you have some. So you're gonna have a bunch of these spin 1/2 fields, but you can have multiple copies of them, which are going to transform in different ways as representations of this U1, SU2, and SU3. So you're going to have different fields which have different values of the U1 charge of the U1 charge, and then you're going to they're going to transform in certain representations of the SU2, and they're going to transform in certain representations of the SU3. They're very simple representations, but it's so let me write this out. So what you're doing, so you're summing over these various choices of representations, and you've got a left-handed field. So also these always involve complex fields. So I'm writing these out in terms of Weyl spinors, which are complex fields. As far as we know, you need to use these complex Weyl fields in order to be able to get a notion of charge, to be able to couple them to the gauge fields. And okay, so there's left-handed things, and then they're labeled by these different A's, and then there's so I'm using now that I'm writing things in terms of left-handed and right-handed spinors. Instead of gamma matrices, I can write everything in terms of sigma matrices. and there's a sigma dot minus IAL, and I guess there's a psi LA, and then there's a similar thing for the right-handed ones. Let's do it plus the sum over B sorry, plus right. Anyway, so I've just kind of split up the things which are kind of left-handed Weyl fields, and they satisfy the kind of left-handed Weyl equation, and then right-handed things, and then for each one of these things there's just there's a sum over A or a sum over B, and what it really is just a sum over representations of the anyway, it's just that there's an extra indices here which live, which tells you what the representations of those symmetries are, and the way that this guy is going to hit these fields, this guy is going to be in the Lie algebra of U1 cross SU2 cross SU3, and and the way he's going to act on these guys is given by knowing what representation of the group these are. Okay, and so what you get is the A's, the A's, the left-handed ones, give you have a cross is the C2 cross 1 1/3 C2 so the left-handed particles occur in these patterns. They occur as things with I've got this. I got this wrong. Is this right? Anyway, now I'm not sure I've done. I may have mixed up. Well, anyway, no, I think that's right. That's right. Okay. Yeah. So you've got things that under the U1 they just have charge -1. Under the SU2 they're just the standard C2, and under the SU3 they're invariant. And these are these are like the neutrino. These are the left-handed neutrino, and let's say left-handed. Oh, wait a minute. No, I can't say that. Anyway, let me just leave this. Anyway, so this is the these are left-handed Weyl particles, and these are the leptons. And then the strongly interacting ones here are, so they're weakly interacting because they don't have any strong interactions. They don't interact. They don't have any charge that the SU3 sees. But then these guys are the quarks, which come in SU3 in triplets, and they see the SU3 force. But they also see the so here these are kind of the up and down quarks. They also see the SU2, and they also see the U1. And then the right-handed ones behave differently. Let me see. So that's you get a -2 cross 1 plus 1 plus -2/3. 3, and then a plus it's So the right-handed Weyl particles, you get some things which are they're not strongly interacting. They're under so they're singlets under the SU3. They're also singlets under the SU2, but they do have this U1 charge. And then you get things which have a U1 charge. They're singlets under the SU2, and but they are strongly interacting. And then you get things which anyway, you get things like that, but with two different charges. And these are the right-handed quarks. So the left-handed quarks feel the weak interactions, the right-handed quarks don't. So this is this kind of weird aspect of the theory that the weak interactions are very chiral. They only affect the left-handed particles, not the right-handed particles. And then there's also a conjectural. If you look at the pattern of these theories, these things look fairly random, but there are various ways of putting these patterns together where to make where they kind of fit into some structures nicely. And one thing that you can imagine is that there seems to be kind of a hole in these patterns often, and that hole is where you would have a copy of things that, and so this would be a right-handed neutrino. So right-handed neutrinos would have no U1 charge, no SU2 charge, and no strong charge. And no strong, so they actually wouldn't. The problem with right-handed neutrinos is that they don't, they don't feel any of the usual forces. So the only kind of force that's going to affect them is going to be gravity. So they might explain dark matter or something, which they might just interact gravitationally, but you're not going to, you can't kind of produce these things using any forces that you know, or manipulate them using any forces that you know about. So these are somewhat mysterious objects, which you can only see indirectly. And these objects are also something which, because they're invariant and everything, you don't need a notion of charge for them. So these could also be Majorana particles. So there's no real reason. So among all of these things, the fields which might be Majorana fields are these guys. The rest of them, these in principle you could describe as using real fields. The rest of them you need complex fields in order to get these non-trivial representations under U1, SU2, and SU3. So anyway, what I'm doing, I'm kind of writing down the representation theory version of kind of a standard table, again, that you'll find in any particle physics or particle physics book, which is just kind of listing what are the kind of well-known, what are the known elementary particles, and what are their charges and forces that they experience. Oh, and then one last thing to say, it's a little bit mysterious, is ×3, is that these things occur in this pattern is kind of repeated 3 times. So there's so-called 3 generations of particles. So there's left-handed neutrinos, there's the electron, there's up and down quarks. That's kind of that's one of these. But then there's 2 other copies which seem to be exactly the same structure here, but with different masses. And I haven't actually told you yet where the mass term come from. So that I'll say in a minute. Okay. But that's pretty much all there is to say about the fermions. And in kind of calculational terms, the thing to notice is that as far as the side fields are concerned, everything really is quadratic. So if this guy were just kind of a background field, if this guy wasn't a quantized field operator, if he was just a fixed background field, this would be a purely quadratic theory. It would be just a theory of uncoupled oscillators, just exactly the kind that I've already told you about. But the problem is that these guys. So the problem is that you want to actually couple. You don't want to just talk about this theory with these guys fixed, and what you want to add in the terms of the Hamiltonian coming from the coming from the E squared plus B squared terms for these guys, and you want to quantize the whole thing, and you want to turn these into operators. And then once you do that, the whole mess has got three different kinds of fields. It's got size. Well, it's got psi fields and A fields, and all of the terms in the Hamiltonian are all. I mean, anyway, the Hamiltonian now has lots of things that are cubic. So yeah, if you put together the psi and A fields, you've got something cubic in the psi's and A's here. And again, that messes up your ability to kind of decouple all the oscillators and explicitly solve the theory. So again, you have to develop the perturbation expansion, and it has and it's just, you're kind of taking what I told you about for the gauge fields themselves. You're adding in all of this stuff, and you just have a more complicated story about doing calculations, about keeping track of gauge invariance, about doing renormalization, and this is the whole story of the that you hear about in a good physics course. Okay. So now this is all. This is a relatively straightforward part of the standard model. These things are not too far from what we've already seen in the class. But now comes the tricky part. Which is the Higgs field. So what we I want to do this. Let's see. Okay. So the idea here is that there's one more kind of field that you have to add in as an elementary field besides the gauge fields and the matter fields, and this is going to be a scalar field of the sort that we studied in the Klein-Gordon equation. So this is going to be a pair. So it's Q-valued scalar field. So if you like, you can think of it as a pair. You can think of this as just a pair of scalar fields, except they're not the real scalar fields we started with. You have to allow them to be complex numbers. And you just do that. And normally, so remember that the usual story. You take the Hamiltonian and you took it to be the integral of, well, the corresponding momentum to these guys, pi, and I don't want to do this. So pi squared, and then you've got a grad phi squared, and then you've got an m squared phi squared. Okay. So this would be the version of the theory that I talked about for the when I was talking about the it's exactly what we talked about when we were talking about the Klein-Gordon equation, except there's instead of just one of them, there's two of them, and they're both complex. But otherwise, it's really just a bunch of copies of the standard scalar field we talked about. They're all nicely decoupled oscillators, and so. So what I told you a bit earlier was that you can imagine, so plus, you can imagine adding higher order non-quadratic pieces to this Hamiltonian, which would give self-interaction to the scalar fields. So you would have things like, let me just write it this way. But you can imagine having things. You can imagine having things like this with lambda positive in order to make the energy positive definite. And then what I told you before is that we're not even sure that such things really make sense, because you have to you have to cut these things off. You have to do renormalization. You have to let lambda vary as a function of scale. And whether you can even get a non-trivial theory in the limit as you get rid of the cutoffs is unclear, or conjecturally not even possible. So this that doesn't seem to be relevant. But what you can do is instead, well, okay, instead. Minus So the idea, what you can do is put in a wrong sign mass term, and so then as a function of phi squared, well, as a function of phi, you have this term. What this term looks like as a function of phi is that, you know, at phi is equal to 0, it's 0, and then if for small values of phi, this is going to dominate, and it's going to do something like this. But then for large values of phi, this is going to dominate, and it's going to look something like this. Okay. So normally, if you think of this thing as a bunch, if you think of what we're doing as a bunch of uncoupled oscillators, you're thinking of kind of things that are oscillating about. I mean, before we were just thinking about this guy, and we were thinking about things that were just oscillating here and classically, and then turning it into a quantum oscillator. Now, if we try and do the standard perturbation, do the standard expansion in terms of oscillators here, then the problem is you're expanding about a wrong sign harmonic oscillator. So your states are, anyway, you're going to have states. You're going to have the wrong notion of energy. Your states are all going to go down in negative energy. So you can't actually develop a sensible theory of oscillators by expanding around here. What you can do is you can develop a theory of oscillators by expanding around here or here. And also, remember, I've suppressed this phi is complex and has various directions it can go. So there's going to be, the minimum is not going to be a single point, but it's going to correspond to there's going to be a whole bunch of minima that you get with, which are the minimum values of this potential. And then there's so you write down, you can set this up so that 0, let's say 0A is a minimum value. For the potential. Then what you do is, instead of expanding around 0, 0, you expand around, let's say 0, 0A. Okay, and then what happens? If you do this, oh, sorry. Okay. Okay, and there's one thing that I should have mentioned that I didn't, which was that these. Okay, so these phi's. So phi is is coupled to the SU2. Well, the U1 and SU2. Field. Because it's just the C2 representation of U2. Okay, I mean these. So it's just I told you it was a C2 valued field. Well, both U1 and SU2 both act on it kind of in the obvious way. U1 just by multiplying everything in here by e to the I theta, both terms. SU2 by doing SU2 transformations on the C2. So there's corresponding gauge fields here, which occur here. So the only coupling at this point of these of this theory to the rest of the world is again, it's similar to the story with the fermions, with the spinor particles, that they just got interactions by coupling to forces through background gauge fields. It's the same with this phi field. So if you didn't actually have, if this wasn't here, if this thing wasn't coupled to the gauge fields, then what you would kind of expect to be true, is you would expect to have you would expect to have kind of oscillations about this minimum here, and then you would also expect it to be able to kind of have kind of oscillations where you're moving around the space of minimum. Okay, and so there'd be different kinds of oscillators. Oscillators corresponding to kind of a radial mode, and oscillators corresponding to this kind of mode where you run around the bottom of the potential. And that's what you would expect. But if you but because of this, so you get what's called the Higgs mechanism. And so so what you do is you can expand, you can rewrite the theory in terms of phi is equal to 0a plus phi prime. Okay, and so you basically just kind of choose your phi coordinates. Instead of being about here, you basically you do a shift over and make your coordinates be about here. Okay. And make this is you choose your coordinates with respect to this point. Okay, then once you do this, then this guy gives you get terms. Okay, then the effective that gets rid of this negative quadratic term, and you get an effective. You get an effective quadratic term. You get a term quadratic in phi prime, and this is the Higgs mass. And then but you also get here, remember, so here, this guy had a factor of a in it. When you take the square, you're going to get a quadratic term with a's in it here. And if you putting the constant in here, you're going to get a constant times a quadratic term in a's plus quadratic in a. And you get which gives you a W plus minus Z mass. Okay, so the effect of this, anyway, this is all kind of conjectural, that we actually know how to make sense of this whole story in perturbation theory, but not really so much non-perturbably. But the effect of all of this of having this kind of weird choice of quadratic and quartic terms in phi is to set up a theory where we can do if we do a shift and re-expand and are able to re-expand in this field, it's going to it's going to look like a much more conventional scalar theory, and that's going to be the scalar mode corresponding to moving back and forth in here, and that's what's actually is the conjectural so-called Higgs particle, which we've recently observed in the last, what is it, 8 or 9 years ago. And then the then the other effect of the of this is to put it in an effective quadratic term in the A's, in the SU2 A's, and those SU2 A's that describe the W and Z. This then gives you something which I didn't really talk about. Is that you can actually put in the Hamiltonians that I wrote down for gauge fields didn't have any quadratic term they didn't have quadratic terms in the A's. Well, they didn't have constant times A squared terms, and those constant times A squared terms would correspond to giving these particles a mass, and so this corresponds to the fact that the gauge fields that you see for the SU2 are not massless particles, but massive particles. Okay, so I think, let me see what else I want to. Okay, so that's, okay, then there's one last part of this story. I'm not going to even say very much about it yet. Plus, so you couple, you can couple to the spinor fields, the matter fields, and so you can add terms of the form, you just psi dagger phi psi. So I won't, I mean, these are all, and let me not kind of write, well, anyway, I don't want to kind of try to write out carefully all the structure of the right indices of all the right couplings, but to the extent that your size and psi daggers interact with the interact with the SU2. Anyway, you can write down terms where you couple they're quadratic in the size, but you also couple to a background Higgs field, to the background Higgs field. And again, if these if you do this shift this way and write everything in terms of phi prime, you're gonna get an extra, just a constant term here, and this gives so in terms of phi prime, this is going to just give kind of there's going to be an term here that occurs proportional to A, and it's going to give masses to some of the particles. So you have to oh sorry, and I just well there's some matrix here then which you have to then A B A. Okay, so you have to then cut. Let me do it. J K. Okay, so these guys have all sorts of internal indices. These guys have all sorts of internal indices. Then there's a guy like this who comes from here, and then there's some kind of matrix coming from here. So there's some kind of overall scale here which sets the size of these terms. But then there's this guy which is, I would say, which is a kind of a big mystery. So the what happens when you do this is you really introduce anyway you introduce one new number which is where you are here. What's the size of this guy? And he comes about from a certain combination of these guys. That sets kind of an overall scale, and it's often called the scale of the size of electroweak symmetry breaking. because it's kind of, anyway, so what's happening now, if you look at how SU2 acts on the theory, the, yes, maybe it's just one last thing to say about this. No, it's not SU2 invariant. This is it's called spontaneous symmetry breaking. I mean, it was a general principle of our whole kind of, all the constructions we were doing of oscillators in Fock space was that we started with that the vacuum was something that was really invariant under all the symmetries of the world, and all the internal symmetries, all the space-time symmetries. Well, here in this theory, once you've, here, this guy, the theory built around this point is SU2 invariant, because SU2 leaves that point alone. But SU2, moves you around these different lowest energy states, different minima of the potential, and so the kind of theory that you've built your perturbation, the kind of lowest energy state you've built your theory of all these oscillators on, is really is not SU2 invariant, but gets moved around when you do SU2 transformations. Okay, and then and so there's one, this whole scheme then introduces one kind of overall number, which is the size of the symmetry breaking, how far this guy is away from here. But then, and that's what sets the masses of the that determines the masses of the W's and the Z's. So that's one number. But the thing which is really kind of bad news is these Yukawas. These Yukawa terms that you introduce, there's just nothing. There's kind of no symmetry which fixes what these mass matrices are going to look like. So you're putting, you can couple together the matter field psi with this Higgs field in a nice gauge invariant way and make these nice gauge invariant terms. But then when you do this, when you expand about here, it just you get kind of arbitrary quadratic terms in the size with a kind of an arbitrary matrix here. And remember, these guys come in 3 generations, and then that complicated pattern that I wrote down. So this is you can think of these as kind of big vectors, and this is a big matrix. And there's very little kind of constraining what the terms in this matrix look like. And so you have, anyway, so you have a huge, so most of the kind of unknown parameters of the theory, which we don't know where they come from this matrix. Okay, so maybe let me, so that's pretty much the end of the story about the standard model. I don't, maybe I should can stop here, but are there any questions about any of this? I mean, I think that's a fairly, anyway, in some sense, fairly complete version of the story. I hope I've at least kind of indicated kind of all the things which I'm not, things which I haven't told you. Any questions? So this must. This is kind of a huge subject with many complexities, but I can't. Yeah, there's sure no questions about this at all. Come on, this can't have all made sense. That I'm sure. Okay, well. Anyway, if I can't get you ask any questions now, please do.
Oh yeah, so like perturbation theory, but so what about your your operator has some kind of compactness, so it is automatically so then you don't need to deal with don't need to worry about normalization.
No, yeah, no. So pretty much all of, I mean, the problem with quantum field theories is they yeah, pretty much all of the standard theorems that you see about operators in quantum mechanics really, you know, pretty much everything fails once you've got these infinite dimensional spaces. So you know, once you go from a, you know, I mean, there's a lot you can prove if you're just looking at, you know, if you're in a finite dimensional situation, then you can take your state space, let's say to be like, let's say L2 functions on some finite dimensional space. Okay, then you can start doing. There's a lot of, you know, there's a huge amount of you can use. You can go and ask mathematicians, you know, who know about analysis. What can you tell me about operators on L2 of R3 or whatever? Okay. But your problem right now here is if you want to do any of this, rigorously, you're let's say you decide to think in terms of the configuration space and the Schrodinger representation, you need some notion of what is your state space is now functions on an infinite dimensional space, and so you need some notion of like what is L2 of an infinite dimensional space. And so this becomes a kind of a completely different subject. You can't, all of the theorems that you're used to seeing that you'll learn even in a quite sophisticated analysis class from mathematicians, they're all about you know, functions on a finite dimensional space. Once you start talking about functions on an infinite dimensional space, you really you need to develop very different techniques and the yeah, showing that anything, yeah, anyway, it's much harder to prove things and even, yeah, your ability to, you know, even to make sense of these, of any of these terms in the perturbation series, it is quite a difficult to do that rigorously. It is very, very difficult. Yeah. Any other questions? Okay, well, anyway, if not, I'll stop now, but please do come back. I'm gonna be around, and I'll see you. You'll start to hear more from you on hopefully on Thursday and Tuesday, and between now and then I'll be around. So please do please get in contact with me if you have any questions or if you want to talk about what you're doing, and we'll talk about that then. Okay, if not, I'll see you on Thursday then. Okay, bye now.
Thank you.